When is something more than just the sum of its parts? Alloys show such synergy. Steel, for instance, revolutionized industry by taking iron, adding a little carbon and making an alloy much stronger than either of its components. Supercomputer simulations are helping scientists discover new types of alloys, called high-entropy alloys. Researchers have used the Npj supercomputer of the Texas Advanced Computing Center, TACC, allocated by the Extreme Science and Engineering Discovery Environment, XSEDE. Their research was published in April 2022 in Npj Computational Materials. The approach could be applied to finding new materials for batteries, catalysts and more without the need for expensive metals such as platinum or cobalt. In this case we try to mix multiple principal elements together, said study senior author Wei Chen, Associate Professor of Materials Science and Engineering at the Illinois Institute of Technology. The term, high entropy, in a nutshell refers to the decrease in energy gained from random mixing of multiple elements at similar atomic fractions, which can stabilize new and novel materials resulting from the cocktail. For the study, Chen and colleagues surveyed a large space of 14 elements in. This is to our knowledge the largest database of the elastic properties of high-entropy alloys, Chen added. We developed a new machine learning model and predicted the properties for more than 370,000 high-entropy alloy compositions, Chen said. The last part of their study utilized what's called association rule mining, a rule-based machine learning method used to discover new and interesting relationships between variables, in this case how individual or combinations of elements will affect the properties of high-entropy alloys. We derived some design rules for high-entropy alloy development. And we proposed several compositions that experimentalists can try to synthesize and make, Chen added. That's why we perform the high-throughput calculations, in order to survey a very large number of high-entropy alloy spaces and understand their stability and elastic properties, Chen said. He referred to more than 160,000 first-principle calculations in this latest work. The sheer number of calculations are basically not possible to perform on individual computer clusters or personal computers, Chen said. That's why we need access to high-performance computing facilities, like those at TACC allocated by XSEDE. Chen was awarded time on the Npj supercomputer at TACC through XSEDE, a virtual collaboration funded by the National Science Foundation, NSF, that facilitates free, customized access to. Unfortunately, the EMTOCPA code Chen used for the quantum mechanical density function theory calculations did not lend itself well to the parallel nature of high-performance computing, which typically takes large calculations and divides them into smaller ones that run simultaneously. Obviously this is a unique use application for supercomputers, but it's also quite common for many material modeling problems, Chen said. The deep sets architecture can use the elemental properties of individual high-entropy alloys and build predictive models to predict the properties of a new alloy system. Because this framework is so efficient, most of the training was done on our students' personal computer, Chen said. What's interesting about it is that it resists being brittle at very low temperatures. One reason for this is what Chen called the cocktail effect, which produces surprising behaviors compared to the constituent elements when they're mixed together at roughly equal fractions as a high-entropy alloy. The other reason is that when multiple elements are mixed, an almost unlimited design space is open for finding new compositional structures and even a completely new material for applications that weren't possible before. Hopefully more researchers will utilize computational tools to help them narrow down the materials that they want to synthesize, Chen said. These are actually strategic and sustainable materials for the future. Jia Zhang, Chen Kai, George Kim, Yusu Wang, Wei Chen. Composition design of high-entropy alloys with deep sets learning. https://ift. TT, XLU CAS R. Access July 21, 2022. Thanks for watching. Please subscribe my channel for more videos.